Okay, so good morning, everyone. I'm Federico, and today I'm going to talk about reinforcement learning. So first we will ask, what is reinforcement learning, of course. Then we will move to asking why and who is using it. And then we will see how one can learn its own reinforcement learning agent, given what's it's outside in the open source community. So what is reinforcement learning? Basically, it can be depicted like in the following figure. So we have an agent that has to take action into an environment, and those actions are conditioned by what the agent sees from the environment, by what it perceives. And essentially, what it does, it's the goal of the agent is to maximize the rewards that the environment gives to it. And the reward is just a learning signal, so it's a number, and it's telling how good or bad the action that the agent has taken was. Okay, so that is the overall intro about reinforcement learning, and this continues endlessly. Hopefully not, because I mean, until the agent has converged to a known behavior. And it's like in a loop. So the agent keeps taking action into the environment gives a reward, and it's changing continuously its states. So given the new observation and the new state, the agent takes again another action, and it keeps going on like that. Okay, so it keeps gathering experiences and use those experiences to improve its own behavior, to solve the task at hand that it's represented by the reward. So if, for example, if we want to train an agent to play the Pong Atari video game, essentially what it does, it's at the beginning of the training, random action. So it doesn't know anything on what is going on, how the world is behaving, and some time passes, so the agent has gathered a lot of experiences, and it starts to understand movement. By the way, the trained agent is the green one in here. So he understands movements and almost understands the velocity, because he needs to know that if it hit the ball with the right angle, it can give it speed, and so it's more probable that it can beat the opponent, like in this case. But it's not quite well trained, this agent, right? By the end of the training, what we want to achieve is that we have like a perfect agent in which he understands perfectly movements and velocity. As we can see, like in here, he hits the ball and he gives it speed, so he can beat the opponent like that. So this is how the training works, and it keeps gathering on and on and on experiences until it becomes very good at what it has been trained. So why reinforcement learning? I mean, there's no, reinforcement learning is one of the three learning paradigms. So the other two are supervised learning and unsupervised learning, right? So why one wants to use reinforcement? And well, it's simple and it's general, because the only thing that the agent needs to do is to maximize a reward. So there's no labeling, there's anything. The only thing that you need is a mathematical function that is the reward, and that's the only learning signal that the agent needs. And if you want to change the task, it's super simple, because you only have to change the reward, right? So you can train an agent to be perfect at beating an opponent, giving I don't know, a +1 reward if it wins the game and a -1 if it loses. But you can have, maybe if we take the example of Pong before, you can give a reward if it hits the ball at a 45 degrees angle, which is crazy, but you can do it, right? And the only thing that you have to do is to change the reward. And so adding auxiliary task is straightforward, because you keep adding those rewards, and as long as the agent is going to maximize those rewards, you can learn new tasks then, like that. So it goes, in its formulation, it has purpose and planning right off the shelf, because when an agent takes an action at a particular point in time, he needs to reason about the future outcomes, right? Because I'm an agent, I'm taking an action right here at this time, and I have to understand that in the future, my action will have some consequences, right? So it's the only training, like learning paradigm in which you can have purpose and planning, which you cannot have like when you have supervised learning and you're training, I don't know, a model to reason about images, for example, right? And then you can have also the ability to incorporate human-like traits, like curiosity, which is something that we have since we are born, imitation, and that kind of field is called imitation learning. And then you can also have feedbacks from the human, so you can have your agent aligned to the human preferences. So who's using it? Well, the list is almost endless, and we have different fields from energy, video games, NLP, finance, robotics, healthcare. But there are some notable examples. So in the video game community, we had StarCraft 2, Dota 2, which the OpenAI researchers has beaten the team champion of Dota 2. We had also MotoGP 19, in which we had, as Orobix, we have developed an intelligent agent to beat the lap time in a MotoGP track. And then last year we had Gran Turismo 7 with Sony researchers. In the NLP field, all of us know the ChatGPT, and it has been trained with reinforcement learning, human feedback, and without that, it wouldn't be able to give us those human-like responses that we know of. And then in the field of the machine learning community and deep learning, there was the alpha tensor, which is the first one that I will talk to you about. And do not be scared about it's essentially what they have done is matrix multiplication. It's like known from a lot of years, right? And there is one algorithm that it's dated 50 years ago, in which essentially you can multiply two by two matrices in 7 steps. So you have to do 7 multiplication, right? And if you're able to find a way to do those multiplications, those matrix multiplication with fewer steps, it means a lot, like, because deep learning is based on matrix multiplication, machine learning, I mean, everything. And so what they've done, the key insight here is that if you are able to view your problem as a game, you can use reinforcement learning, and this is what they have done. Essentially, they have taken the matrix multiplication problem and they have transformed it into a game, and they've used basically alpha tensor, which was an agent that has beaten the Go champion, which is a chessboard game. And once you can do something like that, I mean, the options are really endless because you can use whatever agent you want. And they, in fact, they have discovered a new way to multiply 4 by 4 matrices. So the known steps were 49, and alpha tensor has discovered a way to do it in 47, which, I mean, we can think, okay, it's just 2 steps fewer, but it means a lot in terms of computational saving, timing, costs, and whatever, right? So this is one of the first example. And the second one is an agent that has been developed by DeepMind researchers. It's called Dreamer because it can dream of future outcomes. And what they've done is that they have trained it to craft a diamond in Minecraft, which is crazy because, I mean, for the agent, it needs to know where to go grab the tools that it needs, how to find it, how to combine it, where they are stashed in the inventory, and something like that. So it has a lot of planning, as we have talked before. So you need to know what you are doing now because the overall goal is, I want that diamond, right? So it's super crazy and it's super cool, this one too. And the other one is the training procedure that has been used to train ChatGPT, which is reinforcement learning human feedback. And this is like divided into 3 stages. And the key insight here is that the agent can be anything. Like in this case, the agent is a language model, and a language model is just a model that is trained to generate sequences, right, in a natural language. And what I've done is that the needs was, okay, how can I have my language model to answer me or to summarize some text as a human? So from what we have said, we need a reward, right? How can you mathematically define be like a human? I mean, it's impossible, right? So what they've done is that they have asked some humans to rank the generated responses from the language model. And in that case, they have learned what they've called the reward model. So it's a model that it's able to mimic the ranking from the humans. And given that, you have a reward, and you can just use a single, like a standard PPO agent, which was developed like in 2017. It's super basic. And given that, the language model has been fine-tuned to follow the human preferences, right? Which is something that in other fields it cannot be done like that, right? So this is also a nice, cool thing to have. And then there was MotoGP 19, and in our company we have like developed the first deep reinforcement learning solution to like beat the lap time in like Mugello or Jerez or whatever track. And it was super cool and fun because, I mean, human player can have more fun, and it's more engaging, right, from the point of view of the player. So how one can create and train their own reinforcement learning agent? Well, ship your agent with SheepRL, and the QR code is pointing to our GitHub repository. And I mean, it's super easy because essentially with almost like one line in the command line, you can have your PPO agent trained in the Pong environment, which was the one that I've showed you in the first slide. So it has been trained like this. And if you want to run it over multiple GPUs or multiple TPUs or whatever in your clusters of machines, and you can do it with Lightning Fabric, which is another open source project that gives you the possibility to accelerate your deep learning pipeline or whatever on multiple machine and accelerators. And so it's super easy. Also, the code that we have written, we have tried to take like everything regarding an agent in a single folder in the repository, and so you don't have to like jump around the repository and try to understand what it's doing. The interaction with the environment and the agent, it's super clear, so you can have a look. And what we have done is that we have like a couple of two kind of architectures. One is that we have called Decoupled, in which we have like a bunch of processes. Everyone has their own agent inside and different copies of the environment, so that we can run multiple like experiments and gather a lot of experience in parallel. And they talk through the network, so they exchange their experiences through the network, and they are trained with standard the code is written in PyTorch, so we are using like distributed training from PyTorch. And so this one is the first architecture that we have, and we also have another one which resembles more the first slide, in which you have the agent and the environment decoupled, right, separated. So in here you have like one process in which you have all of your environments, and all the other processes are just taking care of the training, so that you can have like your environment that it's running on one machine with, I don't know, a lot of CPUs, and then for the bulk of the training, you can have your own processing in another machine with multiple GPUs, so you can like separate your training, right? But this is all hidden, because it's just like as I've showed you before, like Lightning run model, and then you can tell, okay, run these on CPU and the other one on GPU, so it's super simple. And as last example, we have like trained a Dreamer agent the one that crafted the diamond in Minecraft to play the famous Pac-Man. And also in here, I mean, it sees that it goes like, it's doing random action, right? It doesn't recognize anything, the monsters, and in fact, like it loses badly. Half of the training, you start to understand, okay, maybe if I take the pills, I get more points, but it doesn't understand that the pills give the possibility also to eat monster, right? Because in that case, he's hiding from the monster because he doesn't understand. Well, in the end, it's super cool because it goes straight to the pills, and then it goes chasing monster because he knows that he can like eat them if they are blue, and in fact in here it goes to like, yeah, chasing the monster. And the beautiful thing of dreamers or dreamer is that he can dream, right? So in here what we have done is that we have tried to understand what he's dreaming of. And from what we see, it's like the Pac-Man starts in the bottom right corner, and it dreams to go up over in the right in the top right corner and eat the blinking piece. So this is what the model is dreaming, and it's also super useful to understand like what is thinking. And that's it. Thank you for your attention. Yeah, go ship your agent, whatever you want. And also, I want to recommend another talk from our colleague, Rafik, calling like the controlling the chaos when you have like a lot of experiments in deep learning and you have to run those, how you can do it with Lightning and Hydra. That's it. Thank you.
Okay, thank you very much, Belo. Great talk. So we have some questions. The first one is, just one sec. Okay, so how difficult is to design a good reward function compared to labeling in supervised learning?
That's a great question because it's super difficult. I mean, the thing is that if you have something that can be like mathematically defined, it's super easy. So for example, when we have done the milestone experience, there were a lot of rewards that can be computed. Like if I go out of track, it's something that you can measure, right? But when you start to think about like the styling guide of the NPCs, that is difficult. It's like asking a language model to be a human. You cannot like quantify it. So there are some solutions to that. So you can use like imitation learning. So you can give the agent a bunch of demonstration, and the agent tries to mimic essentially your demonstration. Or you can have the human feedback. If you don't have something to quantifiable, you can have like, you can align to the human preferences, and you can have a designer saying, okay, look, I prefer this styling guide with respect to that one. And then you can like inject your own preferences, because otherwise there's no, I mean, it's super difficult to come up with a reward, yeah.
Okay, thank you. Second one. So in the example of MotoGP, the difficulties of the game, like beginner, normal, or expert, are based on how much time the agents have been trained?
No. So the agent has been trained to compete and to be like almost superhuman, and then I think that they have done something in like a post-processing on the agent behavior to so that it doesn't beat like the human every time. But this can be another solution. So if you want to have like an agent that is quite well, maybe you can like stop the training, not at the end, but maybe tre quarti, non so come si dica.
Okay.
After the half training, maybe you can stop slightly before, so you can have a not full trained agent.
Okay, we have a lot of questions, great. So aren't there inherent risks and pitfalls for reinforcement learning-based agents when modeling the reward is non-trivial, like reward hacking in Coast Runner from OpenAI?
No, sorry.
Okay, maybe if the one who asked questions want
here.
to elaborate.
Yeah,
Okay.
it was actually me. I don't know if you saw the simple like use case of not use case but showcase of reward hacking. So when like an agent tries to basically like we specify a reward, like finish the GP the what's called like the MapGP phrase message.
Okay.
But maybe the agent like you specify some form of reward, and maybe the agent does that by I don't know like looping on the box.
Yeah, it's really cool. In fact, that is one of the use case in video games for like automatic testing. So when you know that your agent is hacking your word or whatever, it means that it's something going wrong, right? Because I mean, the only thing that it knows, the agent, is I have to maximize the reward. And if I have, I mean, if I win the lab because I don't know, I go underground and then reappear from somewhere else, it's a problem. And so you can use those reward hacking to understand what is happening both in your environment or in your agent. So
Are there ways to detect it without like looking at what the model is doing?
I don't know. I mean, here, I don't think so. You have to look, yes, at what it's doing, and maybe if you can track rewards, or if you have something that you can measure, like in the MotoGP track, you know that maybe a track is long 5 kilometers or something like that. If he completes a lap in 2 kilometers, there's something wrong, and you say, okay, wait, and then you can inspect or something like that.
Okay, then how long does it take to train an agent like Pac-Man to finish the game? And how far in the future is he dreaming?
Okay, so it takes a long time because, I mean, for Dreamer, it's a pretty huge model, so it has a lot of components because it has to understand word models. So we have like recurrent layers, like LSTM, so we have a lot of MLPs and stuff like that. So the training itself, it's fast, because if you can run it on a modern GPU, just one single epoch, it takes seconds, right? But the huge time that we spend is the interaction with the environment, because in that we don't have any control, right? Because the environment is given and it runs on CPU, and so you just have to wait. And so for Dreamer, it takes like a long time. So like we have run experiments, and I think that Pac-Man is already like it's going on. But to reach that point, I think 2 days on 2 GPUs, something like that. And the next.
How far is it dreaming in the future?
How far is it dreaming? There is hyperparameters that you can control. So during the training, you can set the horizon, and we have set it to 15 steps, so it can dream 15 steps ahead. So, and that is what we have plotted there. So it was dreaming like 50 steps ahead, but I don't know. We can also try to let it dream for more and more, but we haven't seen. So it's something that you can control.
Okay, great. Then the next question is asking you if you know Voyager, that is an open-ended embodied agent with large language models showcase the possibility of gradient-less in-prompt RL in GPT-4. Have you seen it?
What it's called?
Voyager.
Nope. No. Is it here? The one?
No, it's always me.
Okay. Okay. No.
It's a paper that has been released like a couple of days ago, but made like super splash in Twitter and reposted it.
Wow. No, I haven't. Can you send me the paper?
Yeah.
Okay.
Yeah, the nice stuff is they basically do RL without ever training the GPT, for instance. They just like basically do RL on the prompt.
Wow.
And it can learn how to play Minecraft like really well. And I think it beats Soda. So.
Yeah?
Yeah, I think it beats really.
With just a language model?
Yeah, with just the prompt of language model, without ever updating the weights. They just train basically everything inside the prompt.
Okay.
Yeah.
Wow. Yeah. Give me the paper.
Yeah.
Okay, great. Last question is, can I use SheepRL, so your platform, to train the agent against itself? For instance, about the Pong game, can the opponent be a different instance of the same agent?
I don't know if in Pong you can do it, but yes, I mean, if you want to implement your, like, it's called multi-agent reinforcement learning, in which there are a bunch of agents, both cooperating or they are one against each other in the environment. So you can also have something like this, and they can like share a policy, so a behavior or not. So if you, I mean, I don't know if the guy is here. No, okay, okay. Okay. So if you want, I mean, if you want to contribute with something like we can have it, but we haven't implemented it yet inside the SheepRL. But once you have it, I mean, as long as you have an environment and an agent implementation, you can do whatever you want, essentially. So it can be done.
Okay, great. I think there are no more questions, or if someone here wants to ask a question, we have a couple of minutes maybe. Okay, otherwise, thank you, Belo.
Yeah,
great talk.
thank you too.
And thank you, everybody.